Good afternoon to everybody. Okay, so I think today we'll be talking about degenerate perturbation theory, and as we have already gone through non-degenerate perturbation theory, in which we calculated the energy eigenvalues due to the perturbation and energy eigenvectors due to the perturbation. Now, as we know that what degenerate perturbation means, it means corresponding to each energy eigenvalue, you have a range of energy eigenvectors. So if I start with an unperturbed Hamiltonian, say H naught is my unperturbed Hamiltonian, and if we execute perturbation to this Hamiltonian, so that the total Hamiltonian is H naught plus HP, where this HP is over, this is our Hamiltonian operator in terms of perturbation, and this is our total Hamiltonian. Now, if we take on, if we stand to define an eigenstate, say psi of n, as a linear combination of some unperturbed state, say A alpha psi n alpha, where this alpha is, it gives us the measure of the set of quantum numbers. And this alpha can range from 1 to f. So inculcating the f-fold degeneracy in our system, f-fold degeneracy. Now, to move on from here, if we see this perturbed Hamiltonian HP, for all Hamiltonian, you can write down this in terms of our. Okay, now, so I'll keep that here. This H is H naught plus HP. All right, if I take the complex conjugate of this eigenvector, I'll take its complex conjugate, and what I will obtain, in this case, we will have psi n star sigma A alpha star psi n alpha star. Alright, that's fine. So now taking the complex conjugate will translate this het of psi n into the broad. So this will be psi n alpha equals sigma A alpha star and bra of psi n alpha. Fine. So that should be clear up to this point. And what we assume here is that this, if I take a couple of states like sine alpha and if I take sine n beta, they are orthonormal to each other so that they are equal to the chronicle delta alpha beta. And psi n, talking about psi n, what we'll have is psi n, if I take the inner product of psi n and psi n, this is going to give me 1. Now, this is our mathematical structure, and we would like to we would like to use this mathematical structure in our Hamiltonian, which is composed of unperturbed Hamiltonian and the perturbation term over there. And one more thing we would like to see here is, we would like to see the measure of this alpha. That we can do is, okay, so if I use for sine alpha here as, this is my sigma, and this alpha would run from 1 to f. Fine, so we will have here A alpha, head of A alpha and alpha star basically, and sine of alpha, and sine of alpha, and then we will have A alpha and sine of alpha as well. Okay, so for this block I can write down this, and for this kit I can write down this, so that this inner product is equal to 1. Fine. So this sigma, as is understood, it runs from alpha equal to 1 to f. So that should be already taken into consideration. Now from here, what we will have is we will have, let's move on from here. So I can think of sigma A alpha squared, and we will have sine of n alpha and sine of n alpha equals 1. And this alpha runs from 1 to f. That should be the case, okay? Now, from this, what we will have is that this sine n alpha, sine n alpha, this will give us 1. That means this sigma A alpha squared will give us 1. Okay, that's the point. So this alpha is not 0, and let's take this Hamiltonian in our equation, and let's proceed from here. Now, what should we go with is, we have basically sigma alpha running from 1 to f, and then we have h sine n of alpha is equal to En sigma, I should keep A alpha with it, okay, A alpha and sine of n alpha. Okay, fine, so what should we do here is we should use the value of h, so we will have sigma A alpha times h naught plus hp, and then I have sine of n alpha equals En and sigma A alpha sine of n alpha. Okay, that's fine. Now we can take the product over here, so we will have sigma. It should be understood that alpha runs from 1 to f, alpha runs from 1 to f. So here what we will have is, we'll have h naught sine n alpha, alright, and plus hp and sine n alpha. Fine, so I would like to keep this A alpha on the outer side. This is going to be equal to En sigma A alpha sine n of alpha. Alright, and as you rightly know, we have defined sine n of alpha, sine n of beta equals to chronicle delta of alpha beta. Alright, now this is my equation. Okay, so what I'll do now is I will multiply this equation from both sides by psi and beta. Psi and beta. I will multiply it from the left side. So I have to take the draw. I will multiply sine and beta. Right. So let's do that. I can grab this part. Alright. Fine? Clear? This is all mathematical. Let's see the mathematical structure. Okay, so what's going to happen here? We will have sigma, then we will have sine and beta, and h naught, sine and alpha, then we will have plus, okay, I'll keep a big bracket over here, then plus sine and beta, then HP and psi and alpha. Okay, this is our left hand side, and I can grab this part, alright, and in the right hand side I will have En, of course this is En, then you have sigma, then A alpha, and you have sine and beta and sine and alpha. This is how it goes. Alright? Okay, fine. So moving from here, what we can do is we can write down, this is understood, this runs from 1 to f. In every case, this alpha runs from 1 to f. And for sine alpha, sine beta, we have a chronicle delta. And sine n beta on h naught. Okay, what it will give us, this is sigma alpha equals 1 to f. This will give us En naught. And then we'll have sine n beta and sine n alpha. Right, so this will be our first term. Then plus, you have sine n beta, then HP, and sine n alpha. That should be the case. And then this will be equal to En sigma alpha from 1 to n, 1 to f, A alpha, and sine n beta, sine n alpha. Yeah, that's fine. So now for this we can replace this by the chronicle delta. This is the matrix element of the perturbation that's being introduced. And this will also be written in terms of chronicle delta. So I can grab the upper part. So my equation will look like this. This is sigma alpha equals 1 to f. Okay, so this is En naught delta alpha beta. Okay, that's fine. Okay, I think then this part is not the part of our equation now. And this will remain as H. I would like to write it as HP alpha beta, where this HP alpha beta, this HP alpha beta is the matrix element of sine and beta, then HP sine and alpha. Alright, so this is done, and now this is equal to, so this is En, okay, En sigma alpha runs from 1 to f, then we have A alpha and simply delta alpha beta. Okay, that's fine. So I can grab this part now. We are independent of this part now, and we have an equation. This is a very crazy equation, and but it certainly has a sense. The point is that okay, if I transform this on the other side, what I will have is I will have En, then minus En naught times delta alpha beta. You have sigma for this. Okay, okay, this is equal to sigma HP alpha beta running from 1 to F and running from 1 to F. Okay, fine. Now, if I have to write En, I can write En as En naught, okay, unperturbed, and then perturbed En1. Let's take it to 1. That means if I transform this En naught on the left side, so what will be En1? That will be En minus En naught. So I can impose the first order correction in energy using this equation, because for En minus En naught, I will be using En1. So how would it look like? So we will have sigma and alpha runs from 1 to F, and for this I will use En. So this is En delta alpha beta. Okay, this is equal to sigma, then HP alpha beta. Well, alpha runs from 1 to F. So I can stretch this equation now. I can write down sigma for both as alpha runs from 1 to F. And then I will have HP alpha beta minus En delta alpha beta. I forgot to write down A alpha. You will correct that yourself. You will put that A alpha with it. Okay. So A alpha, because A alpha is not equal to 0. So this is equal to 0. All right. So we can say that we can have this equation like alpha runs from 1 to F, then HP alpha beta minus En delta alpha beta equals 0. Now we can boil down this thing in terms of a matrix, and for that to have those number of roots that will come in solving this equation, what we will have is we will have to have its determinant, the determinant of HP alpha beta minus En delta alpha beta must be equal to 0. So now how this determinant will look like, and it will have a range of roots, and obviously for alpha equal to beta, this delta alpha beta is equal to 1, and alpha not equal to beta, this delta alpha beta is equal to 0. So now let's write down this determinant, at least write it down to make it look so crazy, so long, and so ballistic. So how will it look like? It will look like this. This is my HP. This is my HP11. Then you will have HP12. Then you have HP13, and so on and so forth. Then you will have HP21, HP. This has to be HP12, HP11, HP12, HP13. So here you will have HP22, then you will have HP33. But in every case you will have plus En for diagonal elements, because for them alpha is equal to beta. Now when alpha equals beta, then delta alpha beta will give us 1. So this is HP2 plus En1, HP3, then you will have En1 plus. So this will go like this. and this will go like this, and this whole determinant will be equal to 0. Now, you will have in most of the cases, you will have different values as the roots of the equations will be evaluated. And you will calculate the roots, and roots will give us the measure of different values, and have those different values means degeneracy. So what does that mean? That means when you have a degenerate system and you try to perturb this degenerate system, when you perturb this degenerate system, the degeneracy of the system is removed. It's removed, and your system behaves like a non-degenerate system. So with this, I would like to end this talk.